Okay, so now we're going to look at the practical application of the PI, of the proportional control system we discussed in the last video. And so this is now all been set up, it's been switched on, it's been calibrated, and I'm now about ready to run the algorithm. So the scope has been set for external trigger, so I'm on to your right again. So the external trigger has been connected to from the trigger output of the compass control unit through to the external trigger of the scope, and this has now been set up for external triggering. So, and also I've got two channels on, and I've got channel 1, which is the top trace, is the error signal, and channel 2 is the K times the error signal, which is actually used ultimately to feed into the servo, so for the error to drive the servo. Let's just trigger this and get the scope set up so we can actually try and maximize what's going on here, and we'll just discuss what's happening. So at the moment I've got the K value set to 1, and the channel 1 and channel 2 gain and attenuation are both set to 1. And channel 1 is the error, so this one is the error, as again, and channel 2 is the K times the error, the proportional result. So I'm now going to move the compass to the south position, so I'm going to press 6 on my HMI, which is the options within the proportional control system, and now the compass is going to the 6. I'm going to move this up slightly so we can actually see this in a little bit more detail. And now then, remember from the software you saw that when we actually run the algorithm, we get a trigger from the unit, from the compass control unit, to actually trigger the scope. So let's see what happens, and we're going to enter number 1 on the HMI to run the proportional control. So let's just discuss it in a little bit more detail. So the scope has captured this information, but let's have a look at what's happening. So this is the error signal, and this is the K times the error signal. Now, because K is 1, these two signals should be the same, which they are, which is fantastic, because we're on a 1 volt per division offset here. There's our center line at 0 volts, and it's gone in a particular direction. I think it went in a clockwise direction, which is this positive line here, and it's taken this amount of time. This is on 200 milliseconds per division, and it looks as though it's taken about 0.8 of a second, maybe 1 second, to actually get to a stable state. And what I'm going to do is to actually improve this a little bit more. I'm going to move this trigger point down to this end of the scope so we can maximize this a little bit more. So I'm just going to shift this over here. Let's see, that's delayed so that we actually get the maximum information on here. And I'm going to run the test again. So I'm going to exit from the proportional control, which was still running. I'm going to put the compass back to the south position, like so, and then when I actually now run the algorithm, the scope will re-trigger, and I should see a new scan. There we go. So it looks as though getting back to 0, it is actually taking 1, 2, 3, 4, 5 seconds to get to an approximate north position. Now remember, it is only an approximate north position because the servo is not being driven really hard to get back to that original point. But let's have a look at this this detail here. Notice it's changed direction. This is because it went from its south position and went in the opposite direction, hence the reason it's gone negative. But let's have a look at this detail here and actually say, what is this number actually representing? So what I'm going to do is, we know from the previous information about all of this from previous videos that we have the DAX run plus or minus 512 effectively, and that's for 512 is about 1.25 volts. So that means that you get 2.44 millivolts per degrees. Now, if this was set at 180 degrees right at the start, this number here would actually be that 180 times the 2.44 millivolts will be 0.44 volts at 180 degrees. So I expect this to be either plus or minus 0.44. Well, let's increase the scale on this and just find out whether that's actually the case. So I'm just going to up these to 500 millivolts per division, so we get a bit more gain. And I'm actually going to run the test again. So I'm just going to exit from the algorithm and put the compass back to its south position. And I'm going to trigger the scope again, run the algorithm again. I'm going to go 1. And now, and if we look at this, it is actually pretty much 0.44 volts. So this is actually showing you the real-time maths inside the actual processor. So this is the real error signal. This is 180 degrees, which is represented by 0.44 volts because of the relationship we just discussed, i.e. 512 steps in the DAC equate to 1.25 volts, and therefore 180 degrees or 180 offset is gives us 0.44 volts, and that's what we've got on here. And these two will be the same. So I'm just going to put these back as 1-to-1. There's a reason for doing this, because I actually want to see the maximum 1.25 volts, which is up here somewhere. So we haven't reached and saturated that. So I could actually use the gain control now to actually increase these numbers, so I can actually see what's going on in a little bit more detail. So let's do that. Let's go to exit that. I'm going to change the gain on channel 1, which is the error signal. I'm going to change that to 2. So I'm using option 3, and I'm going to increase the gain. I'm going to do a multiplication by 2, and now I'm going to move the compass south like that, and then I'm going to run the algorithm. So I'm going to go to 1, and so now we've actually seen that this is now increased this. We've got a gain of 2, and this is around about 0.8 volts, only 0.9 volts, which is exactly what we expect. So I've increased the gain. So now that I know I've got a gain of 2, so rather than 2.44 millivolts per degrees, I've actually now got 4.88 millivolts per degrees. We've got 180 degree error, and that equates to around about 0.88 volts here. So that's what we're seeing on the screen. So this just goes to represent what's going on. Now then, this is K is equal to 1. And it's taking approximately, to go back to the fact that it's taken about 5 divisions at 200 milliseconds. So that's around about 1 second to get to a stable point. Well, so let's just make a note of that. So that's about 1 second, and this is on a 1-to-1 ratio on the pulley. So that's 1-to-1 ratio, and it takes 1 second to get to a stable point from trigger with K equals 1. So let's make K equal to 2. So I'm going to exit the control algorithm, and I'm going to reposition the compass back to its south position. And I'm now going to change the K to 2. So we're going to put enter the option number 2. We're going to K is now 2, and I'm going to leave the gain of channel 1 at 2 at the moment, just so we can actually see it in a little bit more detail. And now I'm going to run the algorithm. So you'll notice here that it's actually got to its position a little bit quicker. We've had actually now at a gain of 2, yeah, and we've now taken 1, 2, 3, 4 divisions to get it back to its, which is actually 0.8 of a second, to get back to a stable point, which is absolutely fantastic. So I'm going to make a note of that. So at K equals 2, we've got 0.8 seconds to become stable. So let's now increase it to 3. So I'm going to exit from that, and I'm going to put it back to the south position, which is 6. And now we're going to take the gain, which is option number 2, and I'm going to make this 3 now. So we're in the south position, we've got a gain of 3, and I'm now going to run the algorithm again. So what you're now starting to see is it's taken a similar amount of time. It's actually slightly shorter to get to the south, to the north position. So it's actually more like this is 2, 4, 6, maybe 7, yeah, about 7.7 a second to get to this point. But you'll see there is a slight overshoot or undershoot here. So it's got a slight dip. and it's trying to get there. So the drive on the servo has got much, much harder now, but it's got so hard it's actually starting to overshoot. You can see this is the actual proportional result here. So this is times 3, and let's see, so we've got 180 and times 3, get my calculator here, 180 times 3 is 540. So you'll just start to notice this has got a flat line on it. It's already got to 1.25, yes? So this is actually already started to saturate. So really we could do with putting some attenuation into this signal now, so that we can actually to get rid of this flat line on here. So this is already saturated at 1.25. This is the K times the error, so it's K times this. So I'm just going to put an attenuation of 2 onto channel 2. So let's exit the algorithm, and I'm going to go 4, and I'm going to put in 0.5. Whoops. Let's see. 4 and 0.5. So we've got the attenuation of a gain of 0.5, or attenuation factor of 2, and going to move the compass to the south position again, and I'm now going to run the algorithm, and so you now see that it's actually now reduced this significantly. So we're not actually saturating because this hasn't got past 1.25, but we now know this is actually whatever numbers on here, we're actually seeing a real value. Should be around about halfway, because we're actually driving the servo at its maximum at 540. It's K times 180 at south. So that means it's 3 times 180, which is 540, which would normally saturate the DAC and output, but we've now put a gain or attenuation factor of 2 in it, so it's reduced this by a factor of 2. So it's still allowing us to see the maths in real time, and you can see the little dip there. So so the overshoot. So what we're now going to do is put it back into its south position, and I'm now going to put a K factor of 4 in. So let's put enter number 2, and we're putting K is 4. Let's put K equals 4, K equals 3, and I'm just making notes that it's one oscillation or one overshoot, and we've got around about 0.7 seconds to get to the south point. So so we're now going to put the K, and we're now going to put this onto 4. So it was 3, now we're putting the K to 4, and we're in the south position, and now let's see what happens. So we're now going to run the algorithm. So now we've got K's even larger. Now, similarly to the last exercise where we had 3, we're actually looking around about 0.7 seconds for it to get to the south position, but it overshoots once, comes back, overshoots on the other side, comes back, overshoots again, and then stabilizes. So it's getting there as fast as it can, but it is starting to oscillate a little bit. So let's just keep on doing it. And also note that we still haven't saturated this, because we're now 4 times 180. 180 times 4. 720, so we still haven't, and we've got to divide that by 2 because we've got an attenuation, 360. So we haven't saturated the DACs on here, but it's we've seen real voltages here that are in the maths itself inside the algorithm, and we can actually calculate that from these results. And so I'm going to exit this, and now I'm going to put K is equal to 5. So now 2, and we'll put K is equal to 5, move the compass to the south position, and now let's see what happens. So we're going to run this algorithm, and that's K around about 0.7. How many offshoots do we have? Let's say 1, 2 overshoots on that. So I'm just making notes of this 2 overshoots, And because I'm going to document this for you, and then you can see this in the PowerPoint presentation that you'll get, which is related to all of this. So we're in the south position, and we've got k is equal to 5, and we're now going to run the algorithm. So we're going 1, and let's see what happens. And lo and behold, we've got total instability. I'm just going to exit this to stop it. So hopefully you could see all of that as it's wandering around. So here we can actually see this oscillation. What's really important at this particular point in time is to actually look with Geiger Nichols formulas. One is that the K value when it becomes unstable. So what we're saying is this instability occurs when K is equal to 5. And the characteristics, we've got multiple overshoots, so it's unstable. So I'm just making notes on that. And the time it takes to get to the first north position is around about 0.7 seconds. And it's now totally unstable. But what's also interesting is the time period that exists here. So let's have a look at this in a little bit more detail. So we're looking from the period from you can either look at the peak or the trough, doesn't really matter. But if you look at the peaks here, this is around about 2 divisions. So this is on 200 milliseconds. So it's about 400 milliseconds is the actual period of oscillation. So we're going to write down the oscillation period equals around about 0.4 seconds or 400 milliseconds. So we're now going to repeat all of this. Now this is on a 1-to-1 setting. So what I want to do now is repeat this on the different settings to see how this changes our response time. Because once again, this is about understanding how control systems change depending on the speed at which things can be altered. So I've got it set so that the algorithm is not running. And so what I'm now going to do is I'm going to take this band off, just holding the servo down, putting it onto the 2-to-1 ratio. There we go. So it takes 2 revolutions to get 1 revolution here. And so that's actually going to be much slower response. So let's see what happens. And just let's see, I'll just clear that down. Right, and let's go back to our K equals 1. So this is now, we're running the same thing now, but with a 2-to-1 ratio. So we're now going to put the compass into make sure it's out of the way, south position. And we're now going to change the K, that's option number 2, to 1. So we've now got K is equal to 1. And I'm going to leave all the gain and attenuations as they were in the last one. So the gain on channel 1 is 2, and the attenuation on channel 2 is effectively 2 as well. We've got half the signal. We're now going to run the algorithm. Now this is going to be much slower. So we're now going to run proportional control. And now you're seeing it's really, really struggling. Look at the time now to actually get to the north position. It is huge in comparison. In fact, I'm going to close this up and run the experiment again. So I'm going to exit from that, go to the south position. I'm just going to move that slightly out the way. There we go. And I'm going to now run the algorithm again. There we go. So let's see. So this is on, let's see, half a second per division. I'm just going to bring this back over here to that point. I'm just going to run that again. So X and go to the south position and run the algorithm again. 1. There we go. So now it's taking, this is on half a second per division, so it's 1, 2, 3, 4, 5. It's almost taking about 2.5 seconds to get to its south position. So that's around 2.5 seconds. This is only approximate. This is within the resolution of the screen. I could put a target on this, but this is not really what the experiment's about. This is about demonstrating to you where these errors sort of like exist and how the system works. So we're going to exit that, and I'm now going to increase the K to 2. So we're going to 2, and now put the compass back. Sorry, whoops, I've just messed this up. Let's just do that again. So that's 2, and the K value is now 2. And we're going to move the compass to the south position. Okay, and now we're going to run the algorithm again. So we're going to 1 and run it. So now with this, it's still stable here, but it's taken around about here. We're not far off 3 divisions, about 1.5 seconds, maybe 1.25 seconds to actually get back to this position. So I'm just going to make a note of that, 1.25 seconds. And exit that. I'm now going to make K is equal to 3. So 2, and now the K value is 3. Enter it, move the compass to the south position. And now we can run the algorithm. And we're now taking pretty much the same sort of time, pretty similar to last time. So it's around about, let's see, let's do 1, 2, yes, it is about 1.25 seconds. And obviously we have no oscillation at the moment. Can't see any overshoots on here at all, which was starting to happen in the last experiment. Let's exit that. Now we're going to put K to 4. Let's see, where are we? Option number 2, K is equal to 4, and move the compass to the south position. And when it stopped, we're now going to run the algorithm. And you'll just start to see a tiny overshoot on that. So let's keep on increasing that. So that was K is equal to 4. Same time 1.25, and only a slight overshoot, but very small indeed. X, and we're going to make this now K is equal to 5. So that goes 2, K is equal to 5. We're going to the south position. And then when it's stable, we're going to run it, and we're going to go to 1. Right, and you'll see more distinctly now. You'll see there's just a little bit of a bit there. So we're going to exit that, and let's go to 2 again, and we'll put K is equal to 6. Put the compass back to the south position. Run the algorithm. And you'll see a more distinct peak as we're doing this. I'm just going to exit that. I'm going to change the K again, and we're going to make it 7. And then we're going to run the move the compass south again, so 6. And then run the algorithm. And now you'll see this got a bit of a double pulse here. It's going one overshoot on the other side. So once we get to K is equal to 7, we're getting 2 overshoots. But the time it takes to get to the south position is the same, which makes sense because it's as fast as the servo can drive, and so we'll get there in the same time once the servo is saturated. If it was a linear device, then we would start to see much more varying information, but because this is not a linear device, which is absolutely fascinating, because saturates really early at around about, what from the tests yesterday was about 170 microsecond offset, rather than the 500 microseconds, so it's really interesting this. So we're going to exit now. We were on K is equal to 7, we're going to make K equal to 8, so now 2, so K is equal to 8 here. Going to move the compass south. And I'm now going to run the algorithm. So let's go run 1. And we're starting to get a little bit more unstable, just a bit more of an overshoot. So we can now go exit that. And now going to increase the K to 9 and move the compass to the south position. And there we go. We're going to run the algorithm. And it's getting a little bit more unstable. Let's go X and let's make K equal to 10 now. And move the compass south. And then run the algorithm. You see it's almost totally unstable. I'm going to make it a little bit more. I'm going to make it to 11. So I'm going to move the compass, move that to 11 now. So K is now 11. Move the compass south. And because Geiger Nichols requires you to have an unstable system to work out the integration time. So we're now going to run this and we'll see how unstable it is. And lo and behold, that's awesome. Excellent. So let's do a calculation on this. So there's our oscillation time. I'm just going to increase the time based on here so I get a little better idea. And I'm going to look at the time difference between these. But what's interesting is this is 200 milliseconds per division. And there's my 200 milliseconds, 400 milliseconds is slightly larger. It's about 400, sorry, no, it's less than that. So there's one peak, there's the other peak. So it's about 380 milliseconds. I didn't, so like, it's actually not dissimilar to the oscillation time of the previous example, which is rather interesting. So the oscillation is equal to 380 milliseconds. And that's with K equals 11. So what this is saying is that we've changed the speed of response because of the pulleys by a factor of 2, so it's slow. So this hasn't actually, so your K value has to increase, but interestingly enough, the actual oscillation, the integration time hasn't actually changed a great deal, which is fascinating. So that's worth noting. So let's just put this back as it was here. So we're now going to put this onto a 1 to 2. And whilst I'm doing this, you can think about what might happen. Let's just put that onto the big one here. There we go. There we go. Right, just make sure this doesn't get in the way. And we're going to have to adjust our scope accordingly. So I'm going to put this back to K is equal to 1 again. So we're now on a 1 to 2 ratio. Okay, so we're on a 1 to 2. So 1 revolution of the servo gives us 2 revolutions. So it's going to be much faster now. So we're now going to edit the K value, put it back to 1, put the compass to the south position, and this is going to rocket around like that. So, very, very quick. So let's just run a test and then adjust the scope accordingly. So let's run the algorithm. Whoa, awesome, look at that. And that's actually, this is really exciting because I haven't actually done all of these experiments like this. I've played around with it, but I haven't done this, and this is fascinating. So let me just increase I'm going to reset this back to 0 here and increase the time base and then put this back over to here. There we go. And I'm just going to exit the algorithm, move it back to south. I just want to check that everything's okay. Now then, what I would ask you to think about actually is when you look at this oscillation, just ask yourself, do you think that you would get an overshoot just through the algorithm, or do you actually think you might get an overshoot because of the way in which the servo and the pointer are connected? So just think about the fact that the servo and the second pulley here, so you've got the servo here, the pulley, is connected by effectively a rubber band. So just think about that in terms of what else might be going on in your system. And I'll leave you with that. So we're now in the south position. I'm going to run the algorithm. We're on k is equal to 1. Oh, that's awesome. That is so fast. Right. So, and that's with k is equal to 1. So let's see, what is the time on this? So there's a bit of an overshoot here. I would ask the questions of why is there an overshoot on this. So, and it's happening, this is on 100 milliseconds per division. We're pretty much getting to the south point here within 1, 2, 3, 4, 5, that's half a second. So we're approximately half a second to get to our north position. And interestingly enough, that's exactly where it should be, given that when it was on a 1-to-1 ratio, it took 1 second. So this is all adding up. So I'm going to exit this, and we're going to attempt to make this unstable. So I'm going to put k is equal to 2. So just whilst I'm doing this, just think about what number you would expect this to become unstable. So I'm going to set k to 2, and I'm going to put the compass to the south position. Okay, and now I'm going to run the algorithm. Oh, and it's got, there we go. So, and this is fascinating because this is a massive, massive overshoot. So that was with k, let me just bring out, obviously 2 is too much, so I'm just going to bring that down to maybe 1.5. So let's put k is equal to 1.5 and move the compass back to the south position. And I'm then just going to run the algorithm. I'm just going to hold on to this whilst I'm doing it. And so I'm going to run the algorithm as 1. That's good, right? Okay, so let's just measure that on the scope. So I want to close this time base up because we're obviously running far too fast here. And so exit that, go back to the south position, and then run the algorithm. That's looking good. So it's actually getting to the south position in pretty much 0.4 of a second, and that's with k is 1.5. So this is k equals 1.5, and we are getting around about 0.4 seconds to get to the north position, and then you've got what, 1, 2, 2 oscillations on that, or 3 oscillations, and 3 oscillations. And now what I'm going to do is just make that was 1.5, so x and exit to that. Now we're going to put 2 in, and I'm going to make it 2 for k, and then we're going to move the compass to the south position. And once again, I'm going to hold on to this, and we're now going to go 1. Right, and now we're going to exit from that so we can examine this in more detail. So it's taking, there's our 0.4 seconds to get to the first one. They've got totally unstable. And now look at the peak difference between here and here. This is the period of oscillation, and this is on 200 milliseconds per division. So we've got pretty much 2 divisions here to get there. Once again, it's around about 400 milliseconds. So this is fascinating. So regardless of the ratio and the speed at which it operates, the oscillation still remains the same, which is intriguing. And so I would ask you to maybe investigate that and see what you think. So what we've done here is we've shown how the K can change the control system, and also how we can actually, from the Geiger Nichols requirement of looking at the integration time, we can actually now look at the oscillation, which is what we see here, and determine the period of the oscillation, and therefore that can be fed into the Geiger Nichols formula. But also Geiger Nichols states that if you put, I think, let me just, I know that I've got the document here, I'm just going to see if I can pull it up. I think I've got it. I just need to double check the facts. Yes, okay. So in a proportional control system, Geiger Nichols suggests that you take the oscillation time and you divide that by a half, and that is actually the best value, or the initial value you should use if it's a purely proportional control. So let's just see if that actually does apply. So what I'm going to do then is, we're on a 1 to 2 ratio, and we know we're getting oscillations when k is equal to 2. So what I'm going to do is make the k equal to 1 and see, let's just put that back to a 1. So we're going to go to option number 2, k is equal to, the k value is equal to 1. And I'm going to move the compass to the south position, and I'm just going to hold on to this and run the algorithm. So 1. So that is actually pretty damn good as a k value, first guess value that k should be for a control system using Geiger Nichols formula, because he states that if the oscillation unstable value is whatever it is, you divide it by 2, 0.5 times 0.5. To actually get that k value. So now we've got a pretty good control system. And what I can now do is I can turn this, and you'll see as I turn this base, this compass is trying to get back to its original point, and it's actually working really effectively. So I hope that's all made some degree of sense. I could repeat this for the other settings, but you get the gist of this. I think that's pretty much all we can do for proportional control, and so we're going to leave that now, and then the next 2 videos will be a similar sort of vein, to one with the theory and the software behind it, and the other one with the actual practical application of proportional integral control, PI control, where we will actually start using the values we've got this time round to feed into our PI control system.